For those of you who are joining us, I'm Phil Sherrod, W4PHS. This is a continuation of the extra class math class. And we're going to try to get into more of the concepts rather than calculations today. Has everybody gone out and bought the approved calculators and been practicing calculator steps to calculate things? If I'm successful today, you're not going to need the calculator very much. I'm going to try to teach you how to answer most of the questions by just looking at them. In fact, amazingly, on a lot of these questions, even the polar rectangular coordinate ones, you're going to be able to look at that question and read it and say, oh, there's the answer. You won't even have to put pencil to paper or finger to calculator. Believe me? I feel like a magician who... Well, I'm like a magician who just said, I'm now going to pull a rabbit out of your ear. Okay. Well, let's get back. Let's start at the beginning again and sort of review a couple of things. When you get into the exam room, they won't let you take any paper in with you because you might have formulas written in secret invisible ink. But you can ask for scratch paper, and they will provide you the scratch paper. And by the way, you have to turn the scratch paper in with your exam, so don't draw any ugly pictures of the examiners on your scratch paper. But what I'd like you to do is when you get into that room with your scratch paper, the first thing you want to do is take that scratch paper and write Eli the Iceman. E-L-I-T-H-E. Now, an equivalent way of saying the same thing is current lags voltage. Some of the questions phrase it one way and some of it phrase it the other way, so be sure to look for whether it's leading or lagging before you jump to the answer, because it could phrase it either way. But if you can always look up here, if they say, you know, an inductor, and then they say voltage leads current or current lags voltage, just look up here and figure it out. In ice, of course, we've got I, the current, is in front of E, voltage, so current leads voltage in a capacitor. The next thing I want you to do is remember my little story about Eli working hard to carry that ice up from his truck and getting hot and sweaty because of his hard work and his temperature being positive. So I want you to put a plus sign under Eli. And remember that the ice he's carrying is cold, so you're going to put a minus sign under there. And once you have got that written down, that is going to help you through many of the problems. Inductors have a positive value, capacitors have a negative value of reactance. Now let's talk about impedance sum. Impedance in general, and you write it as the letter Z for impedance, it has two parts to it. It has a resistance, which we'll write as R, and then it has plus or minus the letter J times X, where X is reactance. And we're going to talk about what reactance is a good bit in this class today. So that is the full way you represent an impedance in rectangular coordinates. And we'll talk about rectangular polar conversion in a little while. I think everyone knows what resistance is. It's just the value of a resistor. Let's talk about reactance sum, because that's the sort of strange thing. There are two types of reactance. We've got XL, which is inductive. We've got XC, which is capacitive.
What did you say,
XL? XL is inductive reactance. XC is capacitive reactance. In this expression, XL and inductive, we can't remember maybe whether it's positive or negative, so we look up here at Eli and we say, inductance, that's a plus. And for capacitive reactance, we look up here and say, capacitive C, it has a minus here. So we now remember that inductive reactance is always going to be plus. Capacitive reactance is going to be minus. So anytime you have an inductive reactance, there's going to be a plus sign here. Anytime you have a capacitive reactance, there's going to be a minus sign here in this expression. Any questions so far?
What is R again?
R is resistance.
Okay.
Good old-fashioned, plain, ordinary resistance. This expression for inductance, which we normally think of and use in a complex case, yeah, grab a chair from outside, which we normally think of and use in an AC circuit that has inductors and capacitors, also works in a good old-fashioned plain vanilla resistor circuit. Suppose all we have a circuit consisting only of a single resistor. Still works. Z equals, if this resistor has a resistance R, R plus J 0. There's no reactance because we don't have a capacitor inductor here. So the reactance part of this is 0. The resistance part is R that goes with the resistor. So that is the impedance of a simple single resistor in a circuit. Simple enough? Normally we don't write the 0J because you don't need it, but that is the full way of specifying it out if you want to. And let's look at some circuits and do some impedance calculations here, or representations, maybe a better word for it. Let's start out, let's say we've got a circuit that has only an inductor, and they tell us that XL is equal to 100 ohms. That would be Z equals, there's no resistance, no resistor in the circuit, so that's 0. It's an inductor, XL. We look up here, XL is a plus. So it's 0 plus J 100. Does that make sense? How about this circuit? A capacitor that has an XC is equal to 100 ohms. That would be Z equals, there's no resistance. It's XC, we look up here, XC, that's negative. So that's minus J 100. Everybody with me so far? Now suppose we add a resistor to this. So we've got this inductor, we've got these capacitors, and I'm going to, in series with it, insert a resistor that has 200 ohms. Down here, a resistor that has 200 ohms. So I've got an inductor in series with resistor and a capacitor in series with resistor. What does that do to it? Well, we've got 200 ohms resistance, so instead of having 0 here, the resistance becomes 200, and instead of having 0 here, resistance also becomes 200. So now we have an impedance that has both resistance and reactance. Clear enough? Okay, if you've got this part, we're moving along real well because so much of the stuff is based on this simple thought process of having resistors and capacitors or resistors and inductors in series. Okay, let's move on here a little bit. Now that you're advancing so well here, I'll leave that up for the moment. If you have a circuit that has, and I'll just put a black box here, and it's got, we won't even be concerned with what's in the black box. It's got some number of resistors, some number of capacitors, some number of inductors. Doesn't matter what it is. But we are told that this box has an impedance of Z1. We're given that. We're said the impedance is such and such. And again, that's a certain resistive part and a certain reactive part. And that's connected in series with another black box. Black box number 2 has an impedance of Z2. It's connected with another black box. And that, behind this door, we have Z3. That's a Z. So we've got 3 black boxes, and what we'd like to know is what is the total impedance of these 3 black boxes connected in series. Good news, it's very simple to solve this. The total impedance is equal to Z1 plus Z2 plus Z3. All you have to do is add together the impedances if they're in series. It's more complex if it's parallel, but if it's in series, it's real simple. Just add together the impedances of the things in series. Let's apply that. All right, here's a circuit for you. We've got, I'll draw it up here. We've got a resistor, we've got another resistor, we've got an inductor, and we've got a capacitor, all in series. And I'm going to say this resistor is 100 ohms, this resistor is 200 ohms, the inductor is 300 ohms, and the capacitor is 400 ohms. Just pull some numbers out of the air. They're all connected in series, so we know the formula. All we have to do is add together the impedances. So let's write down the impedance of each. We'll put a little box around each one to make it more like the other thing. So we've got 4 boxes, but in this case we know what's inside the boxes. So now we're going to figure out the total impedance. Start out with box number 1. Z1 is equal to 100 ohms. That's 100 plus J0. Everybody remember that? Pure resistance. Box 2, Z2 is 200 plus J0. Box 3, we have an inductor, Z3. There's no resistance, so that's 0 resistance. It's an inductor, that makes it positive. That's plus J300. We get the last box, the capacitor 400. Z4 is equal to, no resistance in here, 0. It's a capacitor. Capacitive reactance is negative, minus J400. There are the 4 impedances. Now all we have to do to get the total is add them together. When you're adding impedances, you add column by column. There's no carryover between one column and another. Just add this column and add this column. We've got 200 plus 100, so ZT is 300 ohms. 0, 0 plus 300 minus 400 minus J100. Do you see this? A lot of problems on the exam are specified this way. They will say a resistor is in series with an inductor and in series with a capacitor, and then they start asking questions about it. The way to solve that problem is if always to add the resistors together and then add the inductors and capacitor reactance together algebraically keeping track of the sign, pluses and minuses. And as long as you add the resistances and get that total, add the reactance and get that total, that is the total impedance. Everyone with me so far? Great. Now, this is going to be the foundation for a lot of the stuff we do today. So if you've got this, you're in pretty good shape. Now, I want to stop for just a second and talk about reactance a little more and the calculation of reactance. We've got 3 things we're dealing with. We're dealing with resistance, dealing with inductive reactance, and capacitive reactance. Those 3 things occur over and over in our problems. Resistance is real simple. Resistance does not change with frequency. If you want to be super technically correct, practical resistors have some capacitors and some inductance, because like the leads going into them. So at very, very, very ultra high frequencies, there may be some capacitive resistor effect. But for the point of this class, resistance is the same across all frequencies. So in a DC circuit, if it's a 1K ohm resistor in a DC circuit, it's a 1K ohm resistor in a 20 megahertz circuit or a 50 megahertz circuit. Resistance doesn't change with frequency. Inductive reactance and capacitive reactance do change with frequency, and you need to know the formulas for how to calculate inductive reactance and capacitive reactance given a specified frequency. And that's what we're going to learn now. The formula for XL is equal to 2 times pi times the frequency times the inductance L. 2 pi FL. Pretty simple. You know, 2 times pi is about 6.3 times whatever the frequency is times whatever the inductance is. Just multiply them out. The only thing that messes people up here is getting the decimal point right in the frequency and the inductance. If they say something like a 2 millihenry inductor, you got to think, oh, let's see, where's the decimal point in a millihenry? You know, how many zeros are there in there? That's the only hard part of this. Other than that, it's just simple, dang, 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 dang. 4 multiplications and you got it. Very simple. XC is equal to 1 over 2 pi frequency times the capacitance. Same thing, 2 pi FC. The only difference is it's in the denominator. It's just 1 over that. Same basic form of the function, 2 pi FC, 2 pi FL. It's just we have 1 over here. Everyone with me so far? You need to know these formulas. We'll use these on the exam. In fact, later on we'll work some example problems with these things. So XL and XC, when we have a circuit that has, let's say, a resistor in it, an inductor in it, and a capacitor in it, and it's being fed by some, let's say, frequency generator producing a certain frequency, and we can turn the knob and adjust the frequency, this resistance is going to remain the same all the time, but the inductive reactance and the capacitive reactance will be changing as we change the frequency according to these formulas. Now here's an interesting thing. Let's talk, this is not technically part of the talk, but it's a good point to throw it in. Let's talk a little bit about a resonant circuit. I don't want to erase those because we're going to use those here. But let's see, let me draw up here. We've got let's say we've got a signal source that's producing a signal, an AC signal, and it's got a knob here we can turn, and that's going through an inductor and then through a capacitor and then back like that. Simple circuit. It has an inductor and a capacitor in series. When we know that XL is 2 pi FL and XC is 1 over 2 pi FC. And we know from what we've talked about impedance that the inductor reactance is positive and the capacitor reactance is negative. Correct? Everybody with me on this? So if we've tried to figure out, let's figure out now the formula for the total impedance of these two things in series. Well, we know that when you have two things in series, the total impedance is equal to, in this case, it's going to be XL plus XC. Or XL, we could write it out 0R plus JXL and XC. Well, let's do write it out. In fact, it'd probably be clearer. That would be 0 plus JXL, and the capacitance would be 0 minus JXC. So those are the two things we're adding together. Everything clear so far? We've got two things in series. We know the formula. We simply add the impedances. The impedance of the inductor is no resistance plus JXL. The impedance capacitor is no resistance minus JXC. So, what happens if XL and XC happen to have the same value? We start out with XL, it's 0. They cancel out. They cancel out. So if XL is equal to XC, then we're subtracting these two, we get 0. So the impedance comes out no resistance plus J0, no inductance. A circuit that has no impedance, like a circuit that has no resistance, means that the current flows unimpeded. There's nothing to slow it down, nothing to stop it. When this occurs, this circuit is said to resonate. In other words, it's very easy when you hit that frequency for the current to flow back and forth because the impedance turns out to be 0. That is why a circuit resonates at a certain frequency, because the inductive reactance and the capacitive reactance cancel out, and so there's essentially nothing to impede the flow of electricity, so it flows very easily and it resonates at that frequency. So when we put up an antenna and we have some sort of mismatch, the antenna tuner balances it out by putting either a capacitor or an inductor to cancel it out and try to achieve resonance at the frequency that we're transmitting out. That's the whole purpose of an antenna tuner, to balance out the impedance. So a very important point I want you to remember is that resonance occurs when inductor reactance is equal to capacitor reactance. Now that we know that, let's figure out what frequency that would be. Well, what we need is for 2 pi FL to be equal to 1 over 2 pi FC. Everybody in agreement with this statement? We want the inductive reactance to equal the capacitive reactance. This, at whatever frequency this is, where these two are equal, that will be the resonant frequency. If you were in the 8th grade algebra class, you would know how to solve this for F. But none of us are as smart as we were in the 8th grade. So I'm going to help you out. If you do the algebra, and this is simple algebraic manipulation, there's no calculus involved, just a good old algebra. A high school student could do this, might even be on our high school exam. What you turn out with is F equals 1 over 2 pi square root LC. That is the formula for the resonant frequency of an inductor and a capacitor in series. So if you wanted to know what the resonant frequency is, simply take the inductance in henries, multiply it by the capacitance in farads, take the square root of that times 2 pi, and then invert it, and that is the frequency that it will resonate at. That is just a simple solution of having this equal to this. Yeah, if you enjoy math or algebra, solve this for yourself when you get home. See if you get the same formula. Everybody with me so far? Any questions about what we've covered so far? Because we've covered a lot here. You may not realize that we've covered a lot in just a short period of time. We've talked about impedance, we've talked about series impedance, we've talked about computing reactance, we've talked about computing resonant frequency. I think there are some problems about resonant frequency on the extra class exam. I can't remember. I believe they ask you to compute resonant frequency given an inductor or capacitor certain values. How are we doing? Everybody with me so far? By the way, I have a bad tendency, once I get rolling, to forget about breaks. So if someone would raise your hand after about, we've gone for an hour, or you get desperate, and we'll take a break and relax a little bit. But we're really rolling here because we have covered so much already. And we can go back and review this some more later if you need to. But this is fundamental stuff. And having this down, even up to this point, if you didn't get anything else, would help you tremendously in terms of solving these problems. But we're not even close to finish.
Can I ask a question?
Yes.
Probably way ahead of where you're at right now.
Okay.
Based on what you just had right there.
Yes.
For the resonant frequency.
Yes.
Can you use that to build your bandpass filters?
Yes.
As well, for
Yes.
high and low frequency?
Yes. In fact, that's an excellent. I'm glad you brought that up because I was going to discuss that and I forgot. So excellent. Let's go back and look one more time at XL and XC. XL is equal to 2 pi FL. XC is equal to 1 over 2 pi FC. Let's just sort of think about these functions. Notice that XL is 2 pi FL. Let's focus our attention on F. Suppose we have a particular inductor, we've got it sitting there, we're applying a signal to it that we can change. So we can change the F, but the inductor is wired in the circuit. We can't change the inductance, so we can't change 2 or pi. So the only thing we can change is F. What happens as we increase F? What happens to XL as F increases?
Larger.
Gets larger. You see this? So, I mean, it might be like, suppose we had 1,000 hertz. It would be 2 pi times, I'll put the L first, times 1,000. That's if we have 1,000 hertz signal going into it. Suppose we increase it to 10,000. Then we have XL is equal to 2 times pi times L times 10,000. And I think everyone would agree that this is bigger than this. With me? So the important thing here is that XL increases as frequency increases. Everyone in agreement with that? Knowing that.
L couldn't be a negative.
What?
Could L be a negative?
Well, not in a complex impedance it is, but no, not in real life. Inductors are always have a positive impedance. So it always increases with frequency. Now what that means is that suppose we have a circuit here. Once again, I'm going to have a frequency generator that generates an AC signal, and it's adjustable. And it's going through an inductor and then going back. Actually, let me make it, just add one more little thing to it. Let's put a resistor to represent some sort of useful thing that we're trying to control in here. So we've got an inductor and a resistor in series here. We've got a signal generator, and we can adjust the frequency of this thing. Let's think about what happens as we crank up the frequency, turn up the frequency in this thing. Increasing the frequency has no effect on the resistance R. We talked about that earlier. Resistance R stays just the same. What happens to the inductive reactance, XL, as we increase the frequency? It gets bigger. A reactance impedes the flow of alternating current, just like a resistor does. I think everyone understands inherently resistors make it more difficult for current flow through them. The bigger the resistance, the harder it is. It's harder to go through a 1 mega ohm resistance than through a 1 k ohm resistor versus a 1 ohm resistor. The same thing is true for reactance. The more the reactance is, the harder it is for the current to flow through it. Big reactance is like big resistance. It slows it down or impedes it a lot. So what happens is we crank up the frequency. As we increase the frequency, XL increases, which means that this slows it or impedes the flow of current more as we increase the frequency. So if we drew a little plot here, and we had frequency here, and we had current, you know, we put an ammeter here to measure the current flow through this circuit. And we watch the ammeter as we increase the frequency. So we see, what is the current like? Well, as we increase the frequency, the impedance gets larger, which reduces the amount of current flowing because it's harder to get through. So what happens as we increase the frequency is that the current goes down like this. A higher frequency means a greater greater reactance here. Greater reactance impedes more current flow, so the amount of current decreases as the frequency increases. Does this make sense so far? Now, what does that mean? That means that suppose we're trying to filter out high frequencies. Suppose we wanted to pass only frequencies which were below some frequency here we'll call FC, cutoff frequency. If we put an inductor, the appropriate size inductor, as the frequency increases, the inductor will impede the current. So this is what's called a low pass filter, because it's passing, it's allowing through low frequencies, but it's impeding, reducing current if the frequency is high. So this is a low pass filter. Not a very good low pass filter because it passes, it doesn't have any kind of a sharp cutoff. It's a very gradual decrease. But this principle, if you combine more inductors and use the same principle, you can build it up into a steeper, sharper cutoff filter. Now, I'm not sure if it answered your question or not, but this is a low pass filter based on inductor. I won't go through all of this for capacitor, but capacitor is just the opposite. Remember, capacitor was, let me write down here to refresh your memory. Oh, here it is. XC equals 1 over 2 pi FC. Since it's 1 over, as the F gets bigger, the denominator gets larger, and since it's 1 divided by that means that XC gets smaller. Whereas inductive reactance got larger with frequency, capacitor reactance gets smaller as you increase the frequency. So what that means is we have a capacitor here instead of an inductor. We have a high pass filter. It would go up as the frequency, it would pass more as the frequency increased. So we could use this to block low frequencies but pass high frequencies. What if you combine an inductor and a capacitor? You could get what's called a band pass frequency that would go up and then come back down again. That's the basics of filters. There's more to designing filters than that, but that's the concept behind filters using inductors and capacitors. The capacitors pass high frequencies, inductors pass low frequencies. Anything so far? Okay so far? Any questions about this? All right, covering a lot of material here. Now we're going to move on to polar rectangular coordinates and apply this, what we've just learned, to them. When you get into the exam room and you get your scratch piece of paper you can make notes and pictures on, first thing I want you to do is write Eli the Iceman at the top. The second thing I want you to do is to draw a rectangular coordinate system like this. And I want you to label this horizontal axis R, which stands for resistance. You can write in the word resistance, it makes it clearer to you. And up here, I want you to put in plus J, and down here, minus J. This is the J axis, going from plus values to negative values. Is a plus J inductive or capacitive? It's inductive. Right above here, write inductor. Right down here by the -1, capacitor. Actually, I want you to really write this on the paper because you're going to be using this to make it much easier if you can keep looking at this as you're working these problems. So we know that as we go out this axis here, that corresponds to resistance. As we go up here, that corresponds to inductive reactance, XL. As we go down here, that corresponds to XC, capacitive reactance. So for any impedance, I think it also, by the way, is a good idea to mark this off and actually put some lines here. I'm going to do that as best I can. And we'll put some numbers on them so we can work some problems. I may not have gotten that spaced equally. Let's say this is 100, 200, 300, 400, and 500 ohms, and 100, 200, 300, 400 ohms up there, and then the same sort of thing here. It'd be minus 100, minus 200, minus 300, minus 400. It's a good idea. I think it's a good idea to literally do this, because you can then put points on this thing and look at them and they help you think about it. And we're going to do some logical thinking about this before we do any calculations, because if you understand this and understand some principles here, you're going to be able to figure out the answer by just looking at a lot of these problems. The first thing is resistance is along this axis here, the horizontal axis. How about a point over here? What do you think that would be?
No resistance.
It'd be a negative resistance. There are no resistors that have negative values. If you go into an electronics parts store and say, I want a 1K ohm resistor, they'll go back and get one. 1 mega ohm resistor, they'll get one. If you say, I want a minus 1,000 ohm resistor, they will say, stand here, and they will go call them in with the white suits to pick you up. There are no negative value resistors. If there were, we would have solved the energy problems, because instead of dissipating energy when you run electricity, they'd absorb energy and generate electricity. That'd be great. There aren't any negative resistors. So that means that if you have an exam problem that has any spots over here with a negative resistance, those are impossible answers. You can immediately eliminate anything which has points that have negative resistance. You've just solved 1 or 2 problems on the exam. So look at that. Think, where is it? If it's a point on the left side of the axis with a negative resistance, forget it. So now let's look over here. Let's write down our basic representation of impedance. It's equal to R plus or minus J times reactance. We've got R, which is a distance along the resistance axis. We've got X, which is a distance either up or down on the reactance axis. So given any value, any impedance, we can stick a point on this plot. And I think you're actually doing this sometimes will help you solve these problems. Let's take a real simple one. Let's say Z equals 100 plus J 200 and see where that is. We go out 100 on resistance, we go up plus 200, and we put a point there. That point right there corresponds to that impedance. Everybody with me so far? Let's try another one. Z is equal to 200 minus J 300. A negative value of reactance, 200 resistance. So we get out 200 of resistance, we got to go minus 300, so that's a point down here. So you know how to plot things on this plane, and being able to do that is going to help you solve a lot of problems. Let's talk about some special cases. Suppose they say a circuit has a resistance of 300 ohms. There's no capacitor, there's no inductor, it just has a resistance of 300 ohms. Where is the point on this plane that has a resistance of 300 but no inductance or capacitance? You figured it out. It's right here. Because that would be 300 plus J0, no reactance, just 300. So it's a point on the horizontal line, on the resistance line. There are problems, at least one, I think a couple, where they do something like that and they give you resistance and they ask where the point is on this line. If it's a point anywhere off this line, you can eliminate the answer. If there's no reactance, then it's got to be on the resistance line, because there's nothing to make it go up or down, no reactance to go up or down. How about this? Suppose they say this circuit has an inductor, and the inductor has 300 ohms impedance, reactance. There's no resistor. It's simply an inductor that has 300 ohms reactance. Where is that point? Right here. It's an inductor, that's plus. There's no resistance, so we don't go out any this direction. So we go up 300, we put a point there, and that's the inductor. The same thing, it's a circuit with only a capacitor, and the capacitor has 300 ohm resistance. Down here, minus 300. Capacitor is negative. There's no resistance, so we get a minus 300, that's the point.
Do those exist?
Well, the capacitor doesn't have negative capacitance, but we represent a capacitor as a negative J value in an impedance. So in terms of plotting it on here, a capacitor, it's not that the capacitance is negative. It's not like it's a minus 20 microfarad capacitor. It's only when we represent it as a complex impedance that we use our plus or minus sign to distinguish between inductance and capacitance.
A coordinate location.
That's right. It's not the capacitors, there are no inductors or capacitors whose values are negative. There's no negative impedance, or no negative inductance, there's no negative capacitance.
But do we have zero resistance?
You do have zero resistance if there's no resistor. In real and practical circuit, in a actual constructed practical surface, you never have zero resistance because any wire has some resistance. But for these test problems, we assume that connecting wire has zero resistance. So there's no negative, there's no such thing as a negative capacitor or a negative inductor. It's only a way of representing it in impedance. It's only a mathematical construction, a convenience, a way of doing these problems that we plug the value in. But the actual value is always positive. We just put a plus or minus to make it work out in these kind of calculations. Let's look at, so now you know how to plot resistors, you know how to plot inductors and capacitors, reactance on here, and we know how to plot one that has both, go up, out, and up or down. Now, let's think about something here. Now this is where I have a good mind for reasoning, but I have a terrible mind for memorization. So I always am trying to figure out how to reason things out to avoid memorizing them. And I'm going to give you some things here to help you kind of reason things out a little bit. Let's think about this. Suppose we have a general impedance that has a resistor, and we'll say it's an inductor, plus JX. And I want to, just for this particular point, assume that R is equal to X. Could be 100 ohms resistance, 100 ohms inductance, 200 ohms resistance, 200 ohms inductance, so forth. And let's plot the points. Well, we have 100 ohms resistor and 1 ohm inductance, it's a point right here. 200 and 200, point right there. 300 and 300, point right there. 400 and 400, point right there. Do you see a pattern? They are in a straight line. Makes sense, doesn't it? Because if you go out a certain amount, up in a certain amount. Now, suppose we drew a line through this, like that. And we're approaching discussing polar rectangular stuff. But before we get into the actual calculations, I just want you to think about this. When we get into the polar coordinates, the angle is measured from this axis up. Can anyone guess or think what angle this would be? 45 degrees. 45 degrees. Because the total angle from there to there is 90 degrees, right angle. This is going between it, is bisecting that angle, so it's 45 degrees. Does this kind of intuitively make sense that that's 45 degrees? I mean, I don't know what this, I hope there's nothing you have to memorize, that you just kind of, your mind just thinks, oh, well, you know, it's going out and up the same amount, must be halfway between the two, so it's 45 degrees. The same thing's true if we have a capacitive reactance. If we say Z equals R minus JX, this would be X to C, we have points going down there, and we have a line whose angle is minus 45 degrees. Does that make sense? If the capacity reactance equals resistance, that it's going to be 45 degrees. There's a problem. We'll cover it. I think we're going to do some of these problems, but there's one of the problems which says, and they do all this stuff, you add them together, and it comes out to be something like impedance is equal to, 200 plus J200. And they say, they want you to convert it to polar, and they give you various choices. Without doing any calculations at all, no calculator at all, what angle is it going to be? It's 200 and 200. 45. You didn't touch a calculator. You just looked at this and said, oh, resistance is equal to inductive reactance. You go over 200 and up 200, it's 45 degrees. Any answer that doesn't have 45 degrees in it, as a result, you can strike out. You didn't have to do any calculation at all. You just knew it immediately. And we're going to see that once you get rolling on this thing, you're going to be able to do a lot of problems this way, just by looking at them and saying, oh yeah, 45 degrees. Let's extend this just a little bit more. And talk about what happens if we go back to our formula. Z is equal to R plus JXL. And let's think about the case, just logically now, where R is greater than XL. And think about some points. So let's plot some points on here. We'll plot a bunch of points, but we'll always make sure that whatever value of R we have, it's greater than the value of XL. So let's plot some points. Let me erase stuff a little bit here, clean things up. Let's say R is 100 and XL, well, let's make it be easier. Let's say R is 200 and we want something less than that. We'll say 100 for XL. So let's try 200 and go up 100. It's a point there. Let's say R is 300 and XL is 200. Go out 300, go up 200, it's a point about here. Let's say R is 500 and XL is 100. 500 and 100. Let's say R is 500 and XL is 400. Go out 500, go up here to 400. Now, does anybody see a pattern to where these points are falling? Where are they? They are below the 45 degree line. Now, does it make sense why they're below the 45 degree line? Because the 45 degree line, we went out and up the same amount. Well, if we go out further, then we go up, then we're below the 45 degrees. Now, let's see, I want to pause here, make sure everybody gets this before we go on. Or do you understand what I'm saying so far?
I can see it.
Okay, can you say, okay, I want you to feel it here, feel it. I don't want you to memorize. I want everybody to sort of have a good feeling, say, oh, this makes perfect sense, I understand it, right? If the resistance value is less than the inductive reactance, the points always go up then further, then they go up, and so it must be less than 45 degrees, because 45 degrees would be, it was up the same. So suppose they give you a problem, and it says something like Z is equal to 200 plus J100. And they give you various answers. And one of the answers is 60 degrees, and one of the answers is 30 degrees. I don't know whether 30 is the right number, but it can't be 60. Okay, it can't be 60, right? Because that would be more than 45. So any answer that's more than 45 can't be right. There go those questions and those answers. Okay, so we've just knocked out generally half the answers are gone just by doing this thought process, just thinking. And again, if you've got this drawn on your piece of scratch paper and you get a little confused about this, plot the point. Just draw a point. And I think you'll see, now go ahead and when you draw this thing, draw a 45 degree line to help you remember what 45 degrees looks like. And then once you've got the 45 degrees, and you put a point in here, I think you figure it out. All right, the same thing. Suppose we'll turn it around. We'll say if the resistance is less than XL. So that means we go, XL is bigger than R, so we go up more than we go over. So what is the angle going to be? Greater than 45 degrees. You know immediately if the reactance is greater than the resistance, it has to be more than 45 degrees in the answer. So they're going to give you something, and their problem, well, we're going to work these problems, but you're going to get one that's going to have something like, Z is equal to, 200 plus, 400 and J 400. And there are going to be various answers. One of them's going to be 30 degrees, one of them's going to be 60 degrees. And you're going to say, well, it can't be 30 degrees because that would be less than 45. So, must be, we can eliminate anything that's less than 45. Everybody with me so far? You see how it's, once you spring to think about this, a lot of stuff sort of just falls out without doing any calculations at all. You just sort of look at these things, oh, well, it's got to be more than 45, got to be less than 45, kind of stuff. And of course, there's at least one problem, as I said, which will have something like 200 plus 200. Well, they're equal, and you say, they're equal, so it has to be 45 degrees. Now, there may be more than one answer that has 45 degrees, so we have to figure out which one of those two, but we can immediately knock out and think it doesn't have 45 degrees. Everybody with me? You're getting it here? Getting it? Okay, so this is what I'm trying to do, is get you to sort of begin to think about these things rather than doing all the calculations one by one. We can just look at these things and can come up with feeling for the answer, what it's got to be.
What he's getting at is I wasted my trip going back home to get my calculator.
Yeah, that's right. All right. Okay, the same thing is true for capacitance. If we've got something like Z is equal to, let's say 200, better job with the 200 minus J 200. Well, go over 200, down 200. It's going to be minus 45 degrees. If it's a minus here, then it's got to be down on the capacitor side. And if this equals this, it's got to be 45, so we know the answer is minus 45 degrees. Any answer that doesn't have minus 45 degrees has to be wrong. The same sort of thing. Suppose this is minus 400, 400J. So it's over 200, down 400, it's down there. That's more, we have to swing around more. So that's going to be something, I don't know what it is, but let's say, it's going to be greater than 45 degrees. We know that.
Negative.
Negative, yeah, I'm sorry. It's going to be more negative than 45, more negative. So minus 60 might be correct. Minus 30 would not be correct. Everybody got it? This is a great point for a break. Let's stop here and take a break.